So hello and welcome to SDC Verifier webinars. Today's topic is ship design and plate and stiffener buckling according to DNV and ABS rules. Today we're going to use a FEMAP model that represents the part of the ship. It's completely made with plate elements, but stiffeners are made with beams. So if I'm going to hide this plate elements, all the stiffeners in this model are made with beams. All the features which are available, which are shown in this webinar, are available also for SimCenter 3D and ANSYS. We had the previous recordings. We're switching softwares to show that functionality of SDC Verifier is completely the same for all the three programs. So let's go directly to SDC. I'm not going to stop in detail on the menu and the details of the program itself, because we covered that before. If you are looking for an introduction, please hit us an email or look on our website for the recordings of previous sessions and some more information. And of course, it's always possible to arrange a dedicated demonstration of some features if you're looking for more info. So in the reporting part, we have covered the load combinations. But I'd like to get back to this to remind you how easy and convenient it is to prepare the loads and combinations in SDC Verifier. So we're going to extremely quickly set up the calculation. Well, we have several loads in FEMAP. We go to the loads, we have gravity and two ballast loads, two hydro loads. And SDC Verifier automatically reads these loads. And we start with the preparation of individual loads, which are the single load results or step in ANSYS or combination of FEM load and constraint in FEMAP. So what we have to do is prepare these loads. I just select all the FEM loads, select the constraint. In this case, we have only one, and we press Create button. We have 5 individual loads, which are single load results and can be linearly combined into load sets. That's what we're going to do next. We go to load sets part. We can create load sets directly from here, so type in the name and drag the ones we want to have, maybe multiply with some safety factors or add logic, positive and negative. But I will show you how to create multiple. We execute the right click on load sets and select create and edit multiple. Here you can see that in columns we have all our individual loads. So what we're going to do, we are going to add 4 combinations. Just press add. You're also able to import this combinations from Excel or from clipboard, from some spreadsheets, but it's easy to combine in here as well. So I want to have gravity with factor 1 everywhere, and then I want just to include in every load set one single load out of this. I want to put this diagonally, so I use the factor of 1. Of course, in real calculation, you're going to multiply that with some dynamic coefficients and so on. And I can press set to set it for everything, but I can clean it and set diagonally, so I will have gravity plus 1 of loads in each case. Now I press OK, and these 4 load sets are created. And I'd like to create the load group, which will contain the results of all the load sets. So I can execute the same, create edit multiple, or I can just hit this button, add all load sets, and all the load sets are included into our load group, which we will call overall. Sorry for that, overall. Okay, create, and the load group is done. We're going to execute the code checking and calculations on this group. So let's go directly into the code checking, but first of all, we need to run the analysis and solve our job. So I can do this in FEMAP, and I can do this directly from the SDC Verifier. I can select, well, we have only one job, so it doesn't matter whether we click here, we just analyze the job 1. It starts running the calculation, but since we have only 9,000 finite elements and 5 different loads, it's very quick, even on my laptop. Okay, calculation is done. Now we can see that output sets are linked to all the individual loads. And we're ready to go into the checks, but checks are done not on the finite elements, but on the structural members like panels, plates, and stiffeners. So we're going to recognize the structural members out of our FEMAP model. To do so, we are going to run the panel finder, which can be started from the recognition tab in here, or hitting the button panel finder here, or in the model tree we have all the recognition tools and we have the panel finder. Press edit and the panel finder window appears. As with all SDC Verifier recognition tools, it's possible to well, it's necessary to do only one action to recognize everything, is to press find button. So let's start with that. Let's find all the sections, panels, plates, and stiffeners within our model, and then we'll talk a bit about the panel finder. So I'm pressing find, and on our small model, it's going to take around 10 seconds, probably even less. Even if you're having a huge ship models with millions or few millions of finite elements, it's going to take maximum few minutes to recognize everything for the plate buckling within your model. So let's start with the settings of recognition. What do we have in here? We have a selection, so what members, what entities you would like to check for the recognition. We have selected everything. You can define the predefined girders, stiffeners, and borders if it's necessary. If you are missing some girders, or you're missing some, you need to add some dummy elements, or just split certain panels into different plate members. But usually, if all of your stiffeners are modeled correctly, there is no need in that. There is two ways of calculating the dimensions of the plate. So it's I'm going to go to that. Well, let's show it now. So by default, SDC Verifier recognize the longest edge of the plate as the length, and then width is going to be the longest perpendicular to this longest edge. So this is clear with the rectangular elements, and with triangular plates, there might be some questions, and you maybe want to go into another method. We also have a CSR method. In this case, we take the longest edge as, well, the width, the longest edge as L1, and then we divide the complete area of the plate by the longest edge to receive the width of the plate. So this is another option to calculate the dimensions. And what's also important that the calculations are performed on every element if you select such a method. And thickness is important. Thickness is taken directly from each element. So at some points you might have different thicknesses or different elements on your plates. So if you want, it's possible to define a single thickness for the complete plate, but by default it will be taken automatically from the thickness of the element. So this was basically, you can also rename the sections into some longitudinals, decks, and so on. We have sections along X, Y, and Z, so major axes. And then we have custom sections, which are inclined or hull sections, or, well, with the coordinates that are not lying in the global axis. We also can set here some tolerances, so minimum angle between the elements which are going to be recognized as one section or on one plate, and so on. So by default, you don't need to adjust here nothing, just you can rename the section, the default section names, or make a smaller selection for the recognition. Let's preview the sections. What are the sections? So section is a big plane of elements which is laying in one global coordinate. We selected all the X sections, and when I'm pressing the preview, I have to hide these warnings, and these are the sections we have in our model. So all the sections in this part of the ship that we have are recognized within the X. Then we can repeat the same for Y, and we will show we will see the longitudinals. So we highlighted Y sections. We see each of those. And for decks, we have the vertical one. We can preview them, or we can preview only selected, or we can preview highlighted. Let's see highlighted. It gives us an indication where is that in our model. So we have some decks or horizontal sections. And of course, we have hull and some inclined sections, which in this case are going to be called custom. If I select all of them and preview, you see that we have one inclined section and we have parts of the hull recognized as well. If you are setting the different tolerances for inclinations and angle, you're able to recognize any variety and angle of your hull sections. Then all the sections are splitted into panels. Panel is actually a part of the section which is surrounded by other sections or by girders. So if I'm going to select section X1, I will see all the panels of section X1 and so on. So what are we able to do? We can preview them and we can plot them with different colors or even labels of IDs. I'm going to prepare such a plot to show you the panels. So this is the panels which are on our section X1. And then we go into plates. Each panel is splitted into plates. So on panel 1.1, you're going to have plates 1.1.1, 0.2, and so on. So what we can do here, we can select all of them to see if our recognition is done as we wanted to have. So we can go into plotting. Here is already more plotting options. We can plot it with labels of IDs. We can plot it with the amount of corners or dimensions or only length or width or coordinate systems. So let's select the dimensions and prepare such a plot. And this is all the plates which we have recognized and which are going to be used for plate buckling checks. What do we have in here? So you can see each of those are marked with its dimensions, but you cannot see here the wireframe and the mesh. So I turned on the mesh, and now you are able to see that actually each plate consists of 4 to 8 or even more finite elements. And this is very important that you can have a precise mesh, you can have very detailed mesh and very small elements for your general FEA, for strength calculation or displacements or other finite element analysis you want to have. But if it's surrounded by stiffeners or splitted by girders or other sections, it's going to be mesh independently recognized as one plate and will be in these dimensions will be used for plate buckling checks. A few more options I wanted to show you in Panel Finder before we go directly into the checks. You are able to add plate manually. If you think that something is not set as you want it, or if you want to define some plate by hand, you can add plate by pressing this plus button and then define the length and width and C1, C2 coefficients, also as a direction. Well, in 99 or even more % of the cases, you don't need to do that, but you never know, and you need this flexibility to be able to adjust. You can also edit the plate, so you can edit the dimensions by hand. If you think that it should be reduced, you can edit this by hand, and you can split the panel by hand. I'd like to show this to you because it's a nice option. We're slightly short on time. Okay, I'll just show it to you. So you can split the selected plates by nodes. Then you just select 2 nodes on edges of the plate and it's split it by that line. You can split by selecting all the nodes in order, or you can split by elements, just select the elements you would like to have. All the plates, it's possible to copy or paste from clipboard. And of course, you can export the sections, panel, plates, and stiffeners as SDC Verifier component, as FEMAP group, as ANSYS named selection, and so on. The same we have with stiffeners, or all the stiffeners are recognized. We can preview them. Let's preview with length labels, length values. So you can take a look on that and see if everything is recognized properly. These are the stiffeners of X1 section. I will turn on the thickness and you see all of them highlighted on this section. Okay, one more important thing. The recognition depends on mesh and depends on quality of your modeling. So if you have some free edges, plates might not be recognized correctly. So we have this free edge finder. If we run this, we select all the entities and we press find. We will see the zones where we do have some free edges. And if we select all of them and highlight, we can see some areas where we have free edges, and probably there are some difference in mesh, not merged nodes, which ends up into not proper recognition. I have a short slide on this. So when can it happen? It's when two or few elements are connected to one and they are not sharing the same node, or when this mesh does not coincide. So this free edges, it's important. Once again, it's important for the recognition. So it should be fixed if it's necessary, and after that, the recognition should be rerun. So you should press the find button again. Basically, that was one more thing. The last one, I promise. It's filter. So in filter, you can filter out your panels, plates, and stiffeners on each section. We can select one of the plates, for example, or all the plates, and just check if we don't have the plates with undefined dimensions. If we apply this filter, if there is something wrong or something not correct in the recognition, you might have the plates with undefined dimensions, but here we see that everything is fine. And we can check if all the plates are rectangular, for example, or check on the distance length, which is more, let's say, than 3 meters, and press apply, and all the plates are going to be shown which are longer than 3 meters. And from here, you can manually edit these plates. So click the edit button and modify this 3.3 into 2.5 if you believe you shouldn't have longer than 3 meters and so on. So this gives you a complete control over the plates which are going to be used for your calculation. One small question I promised to cover during one of the previous webinars is the plates with cutouts and holes. I just talked to our developers yesterday and asked about this topic. We don't have holes and cutouts taken into account during the recognition right now. But what can I suggest? For now, we just run the analysis as it is. If the plate is having the problems with the plate buckling results already, even without taking the holes into account, of course, it's going to be even worse with the holes. But we're working on the implementation of also of the recognition and definition for the plate, for the cutouts and for the holes. Okay, that's basically it for panel finder, and let's go to the checks. I want to show you how to create two standards today. So in SDC Verifier, to add a standard, you just execute a right-click on standards, go to add, and here we have the list of standards implemented. Let's start with ABS plate buckling. Let's select ABS plate buckling 2014, and a plate buckling wizard appears. Here is several parameters we have to set. There is basically few of them very important ones. I have a slide to explain this. So first of all, we have to define the PR, which is proportional linear elastic limit, which is by default 0.6 for steel, but if you want to adjust it, it's possible to adjust. Then the thickness factor. In both DNV wizard and ABS wizard, there is a thickness factor, so you can multiply all the thicknesses of your model with a certain coefficient, or to increase or reduce thickness, and check what's going to happen in this case. And then what's very important is the possibility to use or not the plate average stress. So here is a checkbox, use plate average stress. And there is basically two options. I have a slide in here on that. Or we can also go into the wizard, and by the informational button, you will see what's the difference between plate using and not plate average stress. So if we are using plate average stress, we are just summarizing the stress over area and dividing by total area, and it results into one buckling factor for a plate. If we're not doing this, we're taking the stress of each element separately, and it results with a plate buckling factor for which we select maximum out of all of the elements. But if we are using this method, and we're going into average, we need to define, are we going with average element stress when we summarize everything, divide by 8, or when we take the minimum element midplane, which ends up with the maximum compression stress over the element. So as I mentioned, two options. If I'm selecting plate average, it's clear on element it's average. If I'm unchecking this box, I have to select, is it average on element or is it maximum compression stress? Also, so let's use average for both checks. Also, we have to be sure that yield is defined for all the materials. If we go in here, yeah, yield is set for all the materials. If you have 0 here, it's good. And we need to select sections for the check. Here are all the sections selected, but you're able to exclude and select only X sections, for example. Doesn't matter for now. Let's select all. I hope the calculation wouldn't be so long. We press OK, and the standard is created. That's basically everything you had to do to set up your calculation. Now, as all SDC Verifier checks, the formulas are open. You're able to edit the checks and see all the formulas. It has a complete list of formulas. You can, you can see the intermediate results. You can select an element and see the calculation of intermediate results for each of them. You can even copy this, save as a custom, password protected, and modify, add something. If you want to build your own checks based on ABS rules, it's also possible. It's never going to be called ABS anymore, but it's going to be called your custom check based on certain standards. So the formulas are open and you're able to see it. There is some descriptions for everything, and you can see the description of the formulas as well. We're going to create a plot in a second, but I want quickly to add the DNV standard and compare it. So we go to standards, add DNV. In here we have quite a lot of checks. We have fatigue, we have stiffener buckling with plate buckling. That's one we're going to use. Also weld strength checks. But let's go for plate buckling. Similar wizard. You need to define the resulting material factor, which is 1.15. Let's reduce it to 1 to have maybe similar results with ABS. Then materials with yield are 0. All the sections are selected. Thickness factor we keep the same. And we use the plate average stress, so we're not using stress on element. Then some coefficients for stiffener buckling, which we don't have enough time to cover today, but here you also see the description of every characteristic you have to define. So we press OK. Two standards are created. To add the standard, we have to execute right-click on to add the results. Sorry, right-click on checks. Go to criteria plot. And we want to plot the buckling state limit for ABS on a default view. Let's edit this view. Let's set a nice view on our model. Maybe and the one from the front. Okay. Select get. And I also want to adjust the local limits. I want to see automatic legend. Okay, done. We can preview. When we're starting to preview, SDC Verifier starts to analyze the check. So the time of analysis depends on how big is your model, how much loads and different combinations you do have in your model. But basically, you can see in here, I selected too much elements. I'd like to go with only one section. Let's select the section X1, press OK, and preview this plot again. And we see the result. Maximum buckling factor is quite low. It's 0.35 in this plate. We can save this plot and run the same analysis for DNV. So we go to DNV, plate buckling, criteria plot. We plot overall buckling factor with the same view, but we just want to change the legend into a certain section. We go, as you can see, all the recognitions are stored separately. So you can go to sections from list and select one section. Press OK, press preview. It will also start the analysis. So as I mentioned, it depends on the amount of elements and the amount of different loads in combination, and of course how on your PC capabilities, but even in my laptop it's quite quick for such a small model. We can see that for DNV the results are slightly higher. The highest utilization factor is 0.54. I need to check if I defined all the coefficients and characteristics in the same way. But if you've set this to, you can easily set up the report. You can go to empty report designer. I've covered this during our reporting webinar, but extremely quick how to make a quick comparison report. We select the plot we wanted, we drag it, we select the DNV plot we created, and we drag that plot, and we just analyze. You can also remove the table of content later. That's basically 2 pictures in our report. So what we have in here, I remove table of content. I'm not breaking the page before this, no. And we have a comparison of 2 standards. The difference is quite significant, but once again, I need to check on the coefficients, and we can export this report into Word document or PDF file and immediately receive a report with your title and the comparison file. So as I mentioned, we just showed how to perform ABS and DNV calculations in SDC Verifier. This was the last session of SDC Verifier webinars in this month. So we have covered the reporting. On 16th of April, we talked about the fatigue. Then we had a discussion of the offshore checks, the API, AASC codes on beams, joints, and plates for the offshore structures. And today we talked about ABS and DNV rules. I hope this was informative for you. I don't know if there was any questions along the way. We are already running out of time. So if there's some questions.
There wasn't any questions.
Okay. I will turn on the slide with my contact details. Please come back to us if you have any more questions regarding the topic. If you would like to have a demonstrations, just send me an email. And if you haven't tried SDC Verifier before and you would like to do so, feel free to request a trial license. And we have a step-by-step tutorials with all the steps covered in details, so you can try it yourself with the help of our support. So don't hesitate to ask for trial. And I hope this was informative for you. I hope you have seen what you were looking for. And that's basically everything for today. Thank you for attending. Thank you for your time, and stay safe. Goodbye.